So the last few topics I want to cover in Chapter 2 are the basic structure of the periodic table and how you can use that to name compounds, specifically ionic compounds, and then we'll discuss the naming of what are called covalent compounds or molecular compounds. But the periodic table has a ton of information crammed into it. This is a colored version that kind of separates some of the important information. So as you can see, beginning in the upper left corner, they arrange the elements in order of increasing atomic number 1, 2, 3, 4, 5, and it goes from row to row down to element 118. Now, this is an older periodic table. I think they've since discovered and named these elements here, but they're not of any real importance to us. As I've said before, really the first 4 rows contain most of the elements we'll discuss, and they're by far the most common elements that compounds on Earth contain. Now, you also have these things called periods, and over here I've numbered the periods with this letter N, and when we get into some chapters coming up, you'll understand what N means. For now, just understand that it describes the size of the atom. So we call this row 1, row 2, row 3, row 4, row 5, and so on. Now in row 6 and 7, they actually have some elements down here removed from the table. The reason why they did that is because these elements here, which are called the lanthanides and the actinides, because the first element in these rows that where this group is removed is lanthanum, and I believe it's actinium, but I'm not positive if that's the right name because I rarely think about that element. But anyway, they're removed because otherwise the periodic table wouldn't fit on a piece of paper. So they're a very special class of metals which aren't very common on Earth. And then you have these vertical columns, which sometimes are called groups or families. And notice there's a couple ways that depending on the source that you look at, there's a few ways that the periodic table is structured. Sometimes you'll see a table, a more modern view would just have the columns numbered 1 through 18, as you see here. And older versions of the table that I kind of still use are, you separate the two main types of elements into 2 groups, an A group and a B group. So this is column 1A, column 2A, 3A, 4A, 5A, and so on over to the noble gases. The reason why we do that is because we generally call these 2 columns and these 6 columns the representative or main group elements, and we call these B elements here and here the transition metals, which they have slightly different properties than the main group elements. The main group elements, we can predict some things based purely on their position in the table. We can predict their ionic charges. We can predict their sizes somewhat reliably, and so on. Whereas with the B elements, it's not so easy to do that. So that's one of the reasons why they kind of separated them out. Now you'll notice in the table as well that the way we arrange the characteristics of an atom is slightly different. The atomic number is on top, whereas in an isotopic symbol, for instance, carbon 12 would be written like this when we write the isotopic symbol. The atomic number is on the bottom in this version, and here in most tables that you'll find, it's on the top. Keep that in mind. And the bottom number in a periodic table is what's called the average weighted atomic mass that I showed you how to calculate with chlorine and hydrogen and a few other elements. I think it was boron maybe in the other video. And that's down here, 12.011. Also observe in this table that the atomic weights are, and sometimes called the molar mass of an element in grams per mole. These numbers are to 4 decimal places here, some are to 2. So in this course, I usually want students to report atomic masses to 2 decimal places. So you'd call the atomic mass of hydrogen 1.01. I usually use 1.008. Carbon, another commonly used element, would be 12.01. It isn't good enough to just call it 12 or 1. because some of these atomic masses are very similar and you need to carry a few extra digits. Fluorine, 18.9984. You could reasonably call that 19.0 or 19.00, and so on. So keep that in mind when you're showing calculations on assignments and exams. I expect you to report at 2 decimal places for most of the elements. And what else about this table? Now keep in mind that these periods have different lengths. The first period only has 2 elements, hydrogen and helium. Now, and this table is color-coded to show you what are called nonmetals, metalloids, and metals. Metalloids are sometimes called semi-metals, and they're along this staircase right here. The second period contains 8 elements, and the third period contains 8 elements as well. The fourth and the fifth period is where you start to get 18 elements across the, because now you have the transition metals, which is a column of 10. It's an area of 10 across, and depending on how you look at it, 6 rows. We usually just think of these 4 rows in a standard periodic table, and many times you can just ignore this part here. And the 6th period actually contains 32 elements. The 6th and 7th periods, if you count, contain 32 elements. You got, because you're including those. So you can see that you can even find on the internet periodic tables where people have turned it into a circle to kind of round it, make these elements over here overlap those. But this is the more familiar version of the table that you should become familiar with. I want you to understand some of the names and memorize some of the names. So this first column, this first family is called the, I'll kind of just use an arrow here this is called the alkali earth metals. Alkali earth metals. These are called the alkaline. It's very similar sounding, but it's alkaline. Actually, it's alkali metals, sorry, and alkaline earth metals. And a lot of these columns don't have names. This has a weird name I won't expect you to remember. But these are called halogens, as in like a halogen lamp or halogen headlight. And these are called the inert gases, sometimes called the noble gases. Noble being, they don't like to combine with anything, so they're snobs. We have, over the last 30, 40 years, actually been able to make compounds that contain noble gases, but they only exist under certain conditions. You wouldn't find a compound of a noble gas floating around in the air that you're breathing. You'd find elements floating around the air. There's a lot of helium in the air, or some helium and other gases, but they're non-toxic. They don't do anything. They just take up space. So learn these names: the alkali metals, the alkaline earth metals, the halogens, and the noble gases. And then later on, we'll learn a little bit about their chemical characteristics. And then, as I said, these are the 2 groups over here are part of the main group elements, and so are these right here. And these are the transition metals right in here, and these are specifically called the inner transition metals. And then along here you have boron, silicon, germanium, arsenic, antimony, tellurium, and astatine in purple, or light purple. Those are a special type of element. They're called metalloids, metalloids. There's some, you might, depending on the book you're looking at, they might be called semi-dash metals. We call them those because they have characteristics physically and chemically that is somewhere between a metal and a non-metal. Silicon is actually, as you know, since you grew up in the computer generation, computer chips are made out of silicon. And the reason why they do that is because silicon can be made into a conductor if you do what's called doping it with certain other elements. And I believe they used to use germanium, I believe, or some of these elements in here, they would add small amounts to silicon and they would turn silicon into a semiconductor, which means it could conduct an electric current for use in computers if you gave it a source of power. But without a source of power, it isn't going to naturally conduct a current like a metal would. Metals are a group, you can see the vast majority of known elements are metals, and they have characteristics like they conduct a current very well. They can be pounded into sheets. They're malleable. They're almost all solids. The only one that isn't a solid is mercury. That's sometimes called quicksilver. It's used in thermometers. We don't use the mercury thermometers in lab for safety reasons because mercury is very toxic. But these have chemical characteristics where they tend to lose electrons. That's why they're almost always positively charged in ionic compounds. These bluish elements over here are called nonmetals, and they generally acquire a negative charge when they form an ionic compound. And these are the elements that are going to be found in what are called molecular compounds. And then the elements in purple here that I just mentioned are somewhere in between nonmetals and metals. So in the upcoming parts of these videos, I will show you how you can use the position of the element to figure out relatively easily the chemical formula of a compound. All right, so let's jump right into it. Let's discuss how ionic compounds are named and structured. So it's almost always a metal and a non-metal. So we'll start off very general and we'll get more specific. So a metal and a non-metal. So it'll be handy when you're watching this or reading the book to have a periodic table handy. So ionic compounds are going to be an element from over here, combining with an element or group of atoms made up of elements over here. They'll very rarely have any of the metalloids, if ever, involved in any of the compounds. Now, one thing I want to clarify is hydrogen. Hydrogen is a non-metal. Hydrogen is one of the 7 elements that naturally occurs as a molecule of H2. Very flammable, useful gas. However, it's put over here in the alkali metal column because it behaves very similarly to lithium, sodium, and potassium in chemical reactions. It tends to lose 1 electron. It only has 1 electron orbiting a proton. So when it forms compounds, it generally will lose that 1 electron. So that's why they put it over here. Just keep that in mind that it should really, if you based it solely on its its other characteristics like physical characteristics, it should be over here next to helium. But this is you'll always see hydrogen put right there in the alkali metal column. So have that table handy when you're watching this video. It might be helpful. And this is the 2 general classes are ionic compounds we're going to discuss. And if you combine a nonmetal with a nonmetal, we're going to call those molecular compounds, sometimes called covalent compounds. And these 2 words, ionic and covalent, are the 2 general classes of bonds that most compounds use. Now, the simplest ion is hydrogen. So hydrogen looks like this. It has a proton with an electron orbiting around it. And if it loses that electron, it will become a bare proton and a free electron. And that free electron can be used to, it'll be donated to another element, or it can be used to conduct a current and things like that. Now, this will be useful when we discuss in a little while acids. Hydrogen ions, which you would call this a hydrogen ion, label it like that, or sometimes H. I sometimes put the charges in a circle to make it stand out, but you'll see it either way. This is used, acids behave by donating protons. So they behave a lot like ionic compounds. That's why I'm going to discuss how to name and recognize acid formulas after I've discussed ionic compounds. So when you have an ionic compound, you can have an element like calcium. Now, what is calcium? Let's just draw a general picture of a calcium ion. If you look in the periodic table, you'll see calcium here. It's got 20 protons and a mass of around 40. So it's got about 20 neutrons. So that's the thing. When I ask you to draw a picture of an atom, you can, for purposes of just drawing how elementary particles, protons and neutrons and electrons, just round these atomic weights off to the nearest whole number. So calcium is 40.08. You can round it off to 40. So one way to draw a calcium ion would be to just draw a little sphere like this. You could draw let me use a different color to make that stand out. You could draw inside that circle 20 plus and 20 N. There's a lot of notation you could use. That represents the 20 protons and the 20 neutrons, and then orbiting around it. Now, this is obviously a very simplistic picture, but around it you can think of a cloud of electrons, and later on we'll get a little more specific, but this is where the 20 electrons are found. And as I showed you in lab, it's more accurate to draw them as a series of orbits, kind of like the sun and the planets, the solar system model. But calcium, elemental calcium, has that general structure, and if it forms an ionic compound, it's going to generally lose 2 electrons, which I'll use that notation, 2e with a superscript negative, and then it acquires a ionic charge. So you'd still draw the number of protons, 20 protons. It hasn't lost any protons. It hasn't lost or gained any neutrons. All that's happened is it's become a little bit smaller. That's not much smaller, but it is a little smaller in reality. And now it only has 18 electrons around it in this cloud. You can think of it as a cloud of electrons. And it's lost those 2 electrons. And now they're kind of waiting to be picked up by something. What would pick them up? What's going to pick them up? Let's make sure that's in the view here. What would pick them up? I'll keep that on the same piece of paper. Okay. What's going to pick them up is an element like oxygen. So I'll draw oxygen over here, and I will draw its nucleus here. I kind of ran out of paper. It's got 8 protons, 8 plus, and 8 neutrons. How do I know that? I just go to a table and I see oxygen has an 8 up here, 8 protons. It has a mass of 15.9994. Round that up to the nearest whole number, which is 16. So that 16 is the sum of 8 and 8, 8 protons and 8 neutrons. And then around this is orbiting a number of electrons, which would be 8 electrons in the cloud. Now don't worry about the relative sizes of these elements. It's not that critical at this time. But it's going to gain 2 electrons, so it generally gains 2 electrons to form a slightly larger negatively charged particle called an anion. That's called a cation. This is called an anion. I'll clarify that for you in a little bit, but it still only has 8 protons and 8 neutrons. But now it has 10 electrons orbiting in that cloud of electrons. So all that's happened is calcium has lost 2 electrons. They're picked up by oxygen, and oxygen becomes a -2 charge. So that you can see that clearly is not a convenient way to represent how an ionic compound would form. I'm just showing you visually how the elementary particles are being transferred. So you could draw this as calcium 2 plus, and it's better to do the number first followed by the charge, and then do the nonmetal would be oxygen with a 2 negative. And then what you can do is easily write the ionic formula as CaO. And that's how so that these 2 would combine into one formula, which we would write as calcium oxide. We don't need to put calcium subscript 1, oxygen subscript 1. That's not necessary. It's understood to be 1 when you write the formula.